So we've just found that the derivative of sine x is cosine x. That's a really good thing to know. We're going to get the derivatives of all the trig functions in this section. And when we accumulate those, there's a little nice space here for you to make a little table. These are going to need to be memorized. So put yourself some little happy stars around here to remind yourself to memorize these. They are pretty important. And we've gotten our first one right here. Derivative with respect to x of sine x equals cosine x. Okay. Now we'll do derivations for these first three, what I tend to call the big three trig functions. We'll derive where those came from in this notes packet. And then the remaining three either show up on your homework or they can be pretty quickly derived by using similar tactics. Okay, so speaking of derivations here, we can't just trust a graph to give us the derivative because my drawing might have not been all that accurate. So we need to come up with a nice solid algebraic or numerical exploration of this, a solid way to find the derivative for sure of the function sine x. So we've got f of x equals sine x, and to truly understand that this has a derivative, to see where the derivative comes from, we're going to go to the definition of a derivative. So we're going to take it back to the limit as h approaches 0, f of x plus h minus f of x over h. And so here in this case, our function f of x is just sine x. So we're going to have sine x plus h minus sine x over h. Okay. Now, for this first term here, sine of x plus h, big reminder, you cannot distribute a trig function. Don't try to do that. It doesn't work that way. This is a trigonometric addition identity that you probably saw in trig. Looks something like this. The sine of a plus b, often we'll learn it that way, or x plus y or something like that. But this is going to be sine a cosine b plus cosine a sine b. And we won't get into the derivation of where that comes from because that is a thing that we do in trig and it takes a long time. But remember this identity, it came back up again here. So ta-da! All right, so for our expression here with our limit, we are going to have, okay, the a is going to be the x and the b is going to be the h. Okay, so we have sine x cosine h plus cosine x sine h. Okay. Oops, almost forgot my minus sine x on the end there. Minus sine x all over h. All right. And now notice that there are a couple terms in that numerator that have a common factor. It's this term and this term. Those both contain sine x. And so we're going to group those guys together. Limit as h approaches 0 of sine x cosine h, oops, times cosine h, there we go, minus 1 plus cosine x sine of h all over h. And then we're going to split this fraction up into two fractions. All right, limit as h approaches 0, sine x cosine h minus 1 over h plus cosine x sine h over h. Okay, so we split the fraction, but remember when you're taking the limit of two things added together, you can add together the limits of each individual thing. So I'm going to shift this just a little bit to put another limit on that second term. Limit as h approaches 0. Thanks, technology. That was super fast. All right. So we can look at each one of these individual limits here, starting with this first one. And notice that as h approaches 0, this term sine x doesn't really care what's going on with h, okay? There's no h involved in sine x, so as h approaches 0, sine x doesn't change at all. So it effectively acts as almost a constant as h is changing. So we end up getting to pull sine x out of the limit as we would a constant, just because it didn't involve the variable that was changing. So we have sine x times the limit as h approaches 0, cosine of h minus 1 over h. Okay, and then in our second limit here, we'll have a similar situation with cosine of x. As h approaches 0, cosine x doesn't care. It doesn't have an h in it, so we get to bring it out of the limit. Cosine x, because it is multiplying the rest of those terms that involve h. So we have cosine x, limit as h approaches 0, sine of h over h. Okay. Now, to bring up an old nice result that we've seen. This right here, we encountered earlier in this class. This is the nice result from section 2.4. Okay, and in 2.4, that used an angle theta instead of h, but the limit as back then theta approached 0 of sine theta over theta equals 1. That was our nice result, that as an angle gets really small, the value of the sine of that angle is basically equal to the angle itself, or their ratio is 1. And so that nice result applies here. It doesn't matter that we said h now instead of theta. It's h approaching 0 sine h over h. This limit is going to come out to 1. Okay. But the other one, this limit here, we don't have as nice of a result for that. So this one here, we're going to go back to an even older technique of approaching limits. You can estimate this limit using a calculator. Okay, by plugging in really, really tiny values of h. Okay, so you might want to go ahead and pause the video here for a second so that you can plug in some different values of h. Remember to do some really, really small positive values and some really, really small negative values. That way you're approaching 0 from both sides. But plug them into this expression here and evaluate that out. see what happens as you get closer and closer to 0. We'll pause for just a sec. Okay, so now you're back and you've estimated this. And as you plugged in smaller and smaller values of h, getting closer and closer to 0, you should find that this limit actually approaches 0 itself. Okay, approaches 0. Okay, so that's how we can numerically investigate that limit. Now we'll come down here and see our results. All right, we have sine x, and then the value of this limit turns out to be 0. And then we have over here cosine x, and the value of this special limit, the nice result, was 1. And so we have sine x times 0 plus cosine x times 1. And so that is going to just equal cosine x. So f prime of x equals cosine x for the original function f of x equals sine x. And so that is now confirmed as our derivative of the sine function. It's the same thing that we found with our graphical exploration, but now we've just done it in a more algebraic and numerical way, so we can feel a little bit more confident about that result.